In this video, we will demonstrate a strange nature of the induced electric field. And the thing is very non-intuitive. The such things you will see which we have never seen before, never encountered in previous chapters. Now this is the circuit. So the circuit has two resistors. The circuit has two resistors, 2 ohm. Say name this R1 and R2. Say R1 equal to 2 ohm and R2 equal to say 8 ohm as in figure. Now there is a magnetic field region. There is a region of magnetic region of time varying magnetic field. Inside it, through the loop rather, that region is shown here. So this is the region of the time varying magnetic field through the loop, so that the magnetic flux changes with time as d phi dt is equal to, let's make it plus say 10 volts. D phi dt is in volts, rather it's voltage. Okay. Now in this circuit, so find the current flow in the circuit. Find current in the circuit. Also find the readings of the voltmeters. Readings of voltmeters V1 and V2. Now I'll draw V1 and V2 here. So there is a voltmeter across this resistance R1, which is V1, and another voltmeter V2 through the resistance R2. So what will be the reading of these two voltmeters? So this was 2 ohm, and this was 8 ohm, and this is a voltmeter. Say that is an ideal voltmeter, so almost infinite resistance. So there will be no branching of current through the voltmeter, and this magnetic field region is there, so that this d phi dt happens to be 10 volts. Now if d phi dt happens to be 10 volts, then there is current in the outside circuit. Current is in this in anti-clockwise direction. So as for ideal voltmeters, there is no branching of current. So we know this integral of E dot dl. Integral of E dot dl is equal to d phi dt. Magnitude only, so that's 10 volts. Okay. Now let's name the points A, B, C and D. Okay. So here see, except the region from A to B and C to D, the rest is devoid of resistance. So we can write here integration of A to B E dot dl plus integral from C to D E dot dl that is equal to 10 volts. So integral a to b E dot dl, as we know from the derivation of Ohm's law, that is the current multiplied by the resistance. So current multiplied by 2, or this is R1, I into R1, plus from C to D it is current multiplied by R2, that is 8 ohm. So that is equal to 10. So implies I is equal to 1 ampere. So we have found out the current. I is equal to 1 ampere. Now we have never seen such a circuit, because in the previous circuits, in previous cases, we have seen KVL working. KVL means the sum of the voltage drops or the voltage gains in a closed loop equal to 0. So sigma of voltage drops in a loop happens to be equal to 0 in the previous cases we have dealt with, but this is not that case. Here we see that, or rather here should we call it voltage? No, voltage term is associated with conservative fields and conservative forces. Potential or voltage. With non-conservative fields and forces, you can't even utter the word voltage. Okay. So, however, this is KVL for you. This integral E dot dl equal to 0 in a loop. That is KVL. That means the sum of the voltage drops and gains in a loop equal to 0. But that was KVL. That was here. Wherever you can apply KVL, this is the conservative. So in this circuit we say KVL is not working. So that is very, very non-intuitive for us. Now, what about the voltmeters? What about the voltmeters? Okay. Let us analyze here for voltmeter V1. So we'll draw only a small part of the circuit. Voltmeter V1. Let's leave the other parts of the circuit. This was 2 ohm and the current passing through it is I equal to 1 amp, and there is the voltmeter V1. Okay. Now we will consider this loop. We shall consider let's see, we will consider this loop, right? So in this loop, actually, that was AB, right? AB, and across a voltmeter, suppose B dash and A dash. So the loop is A, B, B dash and A dash, and again back to A. So in this loop, what is the magnetic flux? 0. There is no magnetic field in any region inside the loop. No magnetic field at all, so no magnetic flux, so no change in magnetic flux, no question of magnetic flux inside the loop. So that means in this loop we can write integral of E dot dl is equal to 0. It's d phi dt. This phi happens to be 0. So that's Faraday's law for you. In this special case, it becomes 0. Looks like voltage law working, not really. because the field is non-conservative in nature. So we see that Faraday's law is more general, and this KVL is only a special case of Faraday's law, when this flux and all those things are zero, whatever. So in this voltmeter, see, there is a very feeble current flowing in the voltmeter. Very almost it's a tiny fraction of this 1 amp current, but still it flows. So let it be I dash, right? So I dash is a feeble current, extremely small current, because the resistance is extremely high. And the voltmeter measures this current I dash into the voltmeter measures this I dash multiplied by the resistance of voltmeter. It doesn't measure potential difference, actually. It measures current multiplied by resistance. For conservative fields, it happens to be equal to potential difference. So it is not that intelligent like us that it will know the field is conservative. The voltmeter does not know whether the field is conservative or not. So it measures current into resistance across it. Okay. So for this loop, A to B, E dot dl plus B dash to A dash. So B dash and B is same point actually, but still B dash and A dash, and then E dot dl, that is equal to 0, because here the magnetic flux is equal to 0. So A to B E dot dl is I multiplied by 2. Now that is I prime multiplied by resistance of voltmeter. Now this thing happens to be 0. So therefore I prime multiplied by resistance of the voltmeter V1, or resistance of the voltmeter, I mean its magnitude actually, right? Don't worry about the sign. Its magnitude is equal to I multiplied by 2. That is I is 1 multiplied by 2, that is 2 volts. So implies the voltmeter V1 reads 2 volts. Now let's go to the voltmeter V2. Neglect that right part of the circuit. This was 8 ohm resistance, and a current through the 8 ohm resistance is 1 amp. The points are named C and D. And there lies the voltmeter V2. Now by similar calculation, we can write that the reading of voltmeter V2 is equal to how much? Current I1 multiplied by 8, that is 8 volts. So literally speaking, what we have seen, so that is an 8 ohm resistance, and this is a 2 ohm resistance, and so across these 2 points we have a voltmeter. When the voltmeter is here, and don't forget, the real culprit behind all these things is the time varying magnetic field. So the culprit behind breaking down our intuition. Okay. right. So when you place the voltmeter here, it will give a reading of 2 volts here. Now the same voltmeter, instead of keeping the voltmeter here, if you shift the voltmeter to the left side, then that means, let me erase this whole thing. Voltmeter, it's no longer there. So you have just shifted the voltmeter from right side to the left side, and suddenly it will so in the display it will show 8 volts. So that is the strange thing. Here you can't say that the voltmeter reads potential difference. No, it doesn't read potential difference. It reads integral E dot dl across the voltmeter. So this is a new thing you have learned today, that voltmeter will give reading, or will display reading of integral E dot dl across the device or across it.